Okay, so today, let's talk about absolute value.
Absolutely not. Oh, little notes I leave for myself.
Okay, absolute value of x. Now I've mentioned a couple things to you about this kind of indirectly already. There's a couple ways we can define absolute value. Let's think about, what does it do? What's the job of an absolute value function?
To show its value away.
Use distance from 0.
Okay, so you can look at it as being the distance from 0 on a number line. So for example, the absolute value of -3 is its distance from 0. Distance is always positive, right? The distance between these 2 points is 3. The absolute value of 3 is 3, right? Its distance is also 3 from the origin. So its job is to take any input and return the positive output, right? So if the input is positive, it doesn't do a thing. If it's negative, what does it do? What are we doing to this -3 to make it positive? Exactly, we're just multiplying by -1, aren't we? Right? So we can look at the absolute value function then. There's really two ways we can look at this. We can look at it kind of functionally. And does anybody remember what the functional definition of absolute value is? So if I want to write down the function that actually produces this behavior, remember what it was? Square root of x squared. Right, and we're going to come back and we'll look at this in a little more detail as to why that works the way it does. It's pretty interesting why that actually works the way it does. But you can see that it kind of, whenever I square something, I get a positive outcome. If I square a real number, and then taking the square root of that's going to give me my positive answer, right? So that's the functional definition of what absolute value is. A lot of times, though, we like to think of it as a piecewise function because the absolute value function does two kind of different, separate things, right? So we can write an absolute value function like this. Now, does that look familiar? Piecewise functions? Probably been a while since you've talked about piecewise functions. When you have a function that's equal to, and then I open up this script bracket like this, it's saying, okay, there could be multiple behaviors going on here. And in this case, there really are three. We can condense it to two. This is how, like in our calculus book, for example, this is kind of the more standard way of defining absolute value. It equals x whenever x is positive. Like we said, it doesn't have to do a thing, right? If we're putting in a positive number, we just get the same number back. Okay? So does that part make sense? If the argument of the absolute value function, meaning what we're putting into it, is positive, it's just x. Just give us back the same answer. What's it going to do if we take the absolute value of 0? Excuse me, yeah, if x is equal to 0, the absolute value of 0 is just 0, right? So that's the output for 0. And what did we say it did if x is less than 0? So it's negative. Jill, what did we say we were going to do? Yeah. We're going to take its opposite if it's negative to make it positive, right? Now in our book, and this is okay to do, in our book they change this very slightly, and they say instead, let's just combine those two, right? Which is okay to do because they're always going to, this is always going to be an endpoint of either one of these two functions. So it's okay to do this. We'll just write this as two pieces instead of three, and we'll say it's equal to x whenever x is greater than or equal to 0, and the opposite of x when x is less than 0, right? Okay, so these are the two pretty important. Those are the two pretty important ways to think about absolute value. And just to refresh your memory a little bit before we move on and talk about graphs of this, there's an important reason for us to remember this one, and it's those missing steps that we talked about. You guys remember talking about that when we talked about how you solve a quadratic equation where you have to square root both sides. Like if we have, for example, something like x squared equals 9, you know what the solution to that is, right? X equals what? Plus or minus 3, good. But the reason we get that plus or minus 3, remember, is the missing steps. That we don't have to show this work every time. But if I square root both sides, right, that's really my first step. And what did we say the square root of x squared was? Absolute value. And we'll talk more about this, probably not today. We'll talk about solving absolute value equations. You know, maybe we'll just begin and just touch on it today, but unlikely, probably tomorrow. And then what's the solution to this going to be? Well, we can kind of just finesse our way through this. If the absolute value of x is 3, what are the values that x could have? It could be positive 3, but it could also be negative 3, couldn't it? So there's where we get our plus or minus from. Okay, so let's talk about the graph of an absolute value function. So if we've got use this piecewise function. What's that going to look like if I graph it? Let's graph each of those two pieces on their domain. So what's the top one going to look like? What's the domain of the top one? Greater than or equal to 0, right? So everything to the right of or including x equals 0. What is that line?
Like that.
Yeah, good. It's just that's the parent function for any line, isn't it? It's just y equals mx plus b, where m is 1 and b is 0. So it's just going to be a diagonal line. Like that, right? Okay, what about the left side? Same line, but opposite slope. So this is what an absolute value function looks like. It's a v. Okay. That's always going to be the characteristic look of an absolute value function. So what we're going to do next is going to be really, really simple for you. Because all we're going to do is we're going to take this parent function and we're going to talk about how we could transform it using the parameters that we've talked about already quite a bit. Right? So let's say we want to do something like this. Let's say we want to graph, that's a good example here. Let's do, so we want to do one like this. How about g of x equals, let's see that, 4 times the absolute value of x minus 5 minus 2. That ought to look pretty familiar, right?
Yes.
Okay, if we wanted to write down a parent function, and this is the way the book does it, but I want to simplify this a little bit. I want to show you a pretty good trick here. The book talks about writing it in this way. Okay, but we've got a trick. You might recall we did a problem a while back where we talked about fitting a quadratic function. Remember we did that one where we had that piece of an arch or something and it was both stretched horizontally and vertically, right? And the first time we did it, we took into account both the horizontal and the vertical stretch. And then we did some algebra and we found out that we really didn't have to do that, right? That there was a characteristic of parabolas that was interesting. Parabolas, a vertical stretch can also become a horizontal compression and vice versa, right? The way a parabola is shaped, stretching it vertically is exactly the same thing always as horizontally compressing it. And compressing it vertically is the same thing as stretching it horizontally. We can show that algebraically, and we sort of did in this way for parabolas. Right, that would be our generic parent or our transformation of the parent function x squared, where what does a do again? Stretch or compress vertically. What's the sign of a do? Reflection, okay. What's b do? Horizontal compression or stretch. Rather than thinking of the sign of b, an easier way to think about reflecting it over the y-axis is just to change the sign of x. We'll talk more about that later. What did h do? Left or right. K was up or down. But remember, these two we could link together, right? We said that a horizontal stretch and compression is identical to a vertical compression or stretch. How do we show that? Well, I guess I wanted to do, I got one thing in the wrong spot there. This needs to be right there. If I split this apart, remember, we said that the quantity a times b squared could be simplified to what? What can I do to that? A squared times b squared, right? So I can kind of distribute that exponent to both parts and get a squared times b squared. So instead of a and b, this time we've got 1 over b times the quantity x minus h. Those are my two factors instead of a times b, right? So I could take this 2, that exponent, and I could just split this apart into a times the quantity 1 over b squared times the quantity x minus h squared plus k, right? Everybody agree? Everybody agree? Because I've got this factor times that factor, and if I take a product to a power, I can always write that as the product of the separate powers, right? It doesn't just work for squares, it works for anything. In general, we can say a times b to the m equals a to the m times b to the m, right? So if I split those apart, what's the advantage? What's the advantage there? Remember, what we're trying to do is we're trying to simplify this transformation so we don't have to have these two separate parameters, a and b, because they really just accomplish the same thing, we said, right? Those are going to be constants, right? Everybody agree? The only variables are x and y, f of x. So what's the advantage? What do you think?
You can simplify A and B.
Say it again.
You can simplify A and B together.
Oh, okay, yeah, look, all I've got here is I've got some number, some parameter a, times 1 over some other constant parameter b squared. What if I just jumble all that up into one big number? I'm just going to get, what am I going to get? A over b squared, right? A times 1 squared over b squared. And let's not call it a over b squared, let's just call it a, right? Be done with it. We don't need to have this. Does that make sense? We don't really have to have this separate. We don't have to have this a and a b for parabolas. I can always instead, always, there's no need for it, we can always just write a parabola in the form f of x equals a times the quantity x minus h squared plus k, where a represents the vertical stretch or compression, but so what? I mean, that's all we need, right? Like we said, horizontal compression is the same as vertical stretch. Okay? A lot easier. We don't have to fit that extra unnecessary parameter. Okay? Can we do the same thing with absolute values? Yeah, we can. Because what do you suppose if I take the absolute value of a product, what do you think I can do? How do you think I could rewrite that? Absolute value of a times b. Just means it has to be positive, right? Take some examples with numbers. What if we had the absolute value of, I don't know, -3 times 4? That works out to be -12, right? Absolute value of -12 is 12. Couldn't I just split that apart? What's the absolute value of 3? -3. 3 times the absolute value of 4. Right? It's always going to work, isn't it? right? If I multiply two factors together, regardless of what the sign is, the magnitude of the number is going to be the same, isn't it? Right? Depending on what the signs are, my outcome might be positive or negative, but if I'm taking the absolute value, it's always positive, right? Okay, so then what can I do with this stuff right here? Should be able to just lump that together, shouldn't I? Right? I should be able to take this function and write that as a times the absolute value of 1 over b times the absolute value of x minus h plus k. And once again, all that's just one big number, right? Just call it a. So even though the book, and this is, I kind of have a little issue with this, with our textbook, I want you to just kind of ignore this stuff when they have you use b, because I don't want you to. You don't have to, right? We can instead, we don't have to write it in that complicated way. We can just write the absolute value function like this. That does everything we need it to do. Okay. What do you think must be true then about absolute value functions? A vertical stretch must be the same thing as horizontal compression. It is. Okay. And vice versa. Is it that way for every function? No, it's not. It's not for every function. But it is for, it happens to be for those two. Okay? All right, so let's try our example then. If we had, I forgot what it was, but did anybody have it written down? Is it a 4 out front?
4, yeah.
Times the absolute value x minus 5? Minus 2? So all we have to do then, we know the meanings of all those parameters. So what are we going to do to our parent function in this case? So we're taking our parent function, which normally just looks like that, right? There's my absolute value function. And where are we going to move it? Okay, right 5 and down 2. Now, what's going to be the recognizable point that we're probably going to track when we move this thing? Yeah, the vertex, right? And this is the point that we call the vertex right there, right? So we're going right 5, we're going down 2, and if we stretch it by a factor of 4, what's that going to do vertically? Yeah, so instead of going over 1 and up 1, I'm going to go over 1 and up 4, right? The vertical component of that movement of our rise over run triangle has to be 4 times bigger. So over 1, up 4. So it ends up looking kind of tall and skinny, right? Like that. Okay, make sense?
Do you need to draw over 5?
Say it again.
Draw it over 5.
Oh, whoops, I forgot to draw it over 5. Yeah, you're right. So, yeah, over 5, down 2, there we go. So we gotta go up 4 over 1, and then back 1. Okay, what do you notice about symmetry of an absolute value function? If we just start with our does it have symmetry?
Yeah.
Okay. It has symmetry. What kind of symmetry?
Vertical lines.
You have vertical line symmetry about what special vertical line? The y-axis. Okay, what kind of symmetry did we call that? Remember, we had 2 kinds of symmetry we talked about. Which one was that? We have folding symmetry about the y-axis. Well, we had even or odd. Remember, I probably should give a bit of context. So we talked about those 2 kinds of symmetries that all functions could have. They don't have to have. Which one was that? Which one?
Even.
Yeah, it's even symmetry. Yeah. Even symmetry. And let's remind ourselves real quick what even symmetry is. Right? Even symmetry says that if I evaluate a function at negative x, Matthew, what do you think I'm going to have to get back? If I go back x, how is that going to be compared to how far up or down I would go if I went over x?
Um,
So like if this is x, that's negative x, right? This must be, if that's the function, this just must be the value f of x, right?
Yeah.
So what would f of negative x have to be for even symmetry?
the
F of x, yeah. Okay, meaning, now think about that. That means that if we go left or right, we should always get the same y value. Isn't that really what you'd have to have that kind of folding symmetry, right? Does that make sense? Does that work? Let's do that test. Let's try, what is the absolute value of negative x? It's x, isn't it? Right? How could I show that? Because once again, I've got a product of two numbers here, don't I? What are the two numbers that are being multiplied when I say negative x? Negative 1 and x, right? So I should be able to split this up into the absolute value of negative 1 times the absolute value of x, and the absolute value of negative 1 is 1, right? So the absolute value of negative x is x, right? Or the absolute value of x, right? So it's even symmetry, good. What happens, we said that, I know that we kind of were talking about it, and once again, we'll just kind of project the way it was sort of discussed in our book here, but we don't really need to, all we need to do, if we want to change the value, if we want to reflect something over the y-axis, we can make this really simple. To reflect over the x-axis, here's the way I've always taught this. I'm just going to do it the way I've always done it. To reflect over the x-axis, all we have to do is replace y with negative y. And what's that mean? So if we have something like, for example, y equals x squared, well then if I want to reflect that over the x-axis, I'm just going to multiply y, which is that whole thing, by negative 1, right? So that would just give me y equals negative x squared, right? Same thing, by the way, as just having a negative a, isn't it? Because a is the number that's multiplied by the whole function. So if a is negative, that's exactly the same thing as just multiplying y by negative 1. See what I'm saying? Okay. How do we reflect over then, by contrast, if we want to reflect over the y-axis, what do you think we do? What do we replace something with something? Yeah, we just replace x with negative x. Exactly. That's all we have to do. Okay. So for example, if I want to reflect the parabola y equals x squared over the y-axis, I would just get the new function y equals negative x squared. Does that look any different? How come? I mean, if I simplify it, it just ends up looking like x squared. How come? What's a parabola look like? If I reflect that over the y-axis, does it change?
No.
Doesn't change at all, right? Okay. But if I do something like, let's say, y equals x cubed. Right, so that's something like that. If I want to reflect it over the y-axis, I would just trade the x for a negative x. And if I simplify that, what do I get? What is the quantity negative x cubed? That just becomes negative x cubed, doesn't it? Right? I could think of that as being negative 1 cubed times x cubed, which is negative x cubed. So if I graph that, that looks like that. Right? So that did do the job, didn't it? Okay. So what about an absolute value function? If I try to reflect that over the y-axis, what's going to happen? Kurt, what's going to happen if I substitute negative x there? Does it do anything? So in other words, what are the math gods telling us? If the function doesn't change when I substitute a negative x, same function, right? Reflects onto itself. Okay? Yeah. All right. See if there's anything else. How much? Why don't we? Let's go to the lab. I'll let you guys work a little bit.